Okay, so last time we introduced the axiom of foundation and proved that the membership relation is well founded on every set. As I said, the motivation behind introducing the axiom of foundation is that we want to avoid certain pathologies, but it's not, that axiom is not really essential in the sense that you don't have to accept it, okay? You can perfectly do mathematics without it, except you have to restrict your attention to those sets which satisfy a consequence of the axiom of foundation. But it's reasonable to ignore this axiom, even though it's common practice to adopt it because we don't want sets behaving pathologically. What do I mean by that? A consequence of the axiom of foundation is the following. There are no sets X such that X is a member of X, okay? And the proof is as follows. Assume to the contrary that there is X such that X is a member of itself. Assume that there is a set which is a member of itself. Now, by pairing X with itself, I can form this singleton containing X. Let this set be Y. By the axiom of foundation, which was number what? Axiom 8? Yeah. Now, this is a non-empty set. Therefore, by the axiom of foundation, it has a member which is disjoint from itself, okay? So this claim is simply by axiom of foundation. If you have an non-empty set, it has a member which is disjoint from the set itself. However, you see Y has only one element. The only member of Y is X, and the claim is there cannot be such Z because there's only one element in Y, namely X, but if you intersect X and Y, you get X itself again. Not X itself, but the singleton containing X, because I assume that X is a member of X, and by construction X is a member of Y. So we have this. Thus, such Z cannot exist, the contradiction. Okay? So, if you have a set X which contains itself, form the singleton containing X, apply the axiom of foundation to this guy, and you'll realize that you get a contradiction. Now, this can easily be generalized. Prove that there are no sets X and Y such that X is a member of Y and Y is a member of X. Or you can prove that there are no sets X, Y, and Z such that X is a member of Y, Y is a member of Z, and Z is a member of X. And this can go on. You can do this with four sets as well. The point is, axiom of foundation prohibits sets from being member of themselves. It prevents such loops. This cannot happen. You cannot go in a loop like this, and you cannot go in a loop like this as well. Okay? Axiom of foundation prevents all these from happening. Okay? So these are not true under the axiom of foundation. Now, if you drop axiom of foundation, there can be such sets. Indeed, I mentioned this last week. There's an axiom called Axel's anti-foundation axiom, and it allows like sets which form an infinite decreasing chain under the membership relation. Again, we'll show that there cannot be such a sequence under the axiom of foundation, but if you adopt another axiom, there can be such sets. The point of the axiom of foundation, as I said, is to avoid pathologies. What kind of pathologies? Pathologies like this. Like, you don't want a set to be a member of itself, or you don't want a set whose only member itself. It just doesn't, well, at least people think that it just doesn't go along with our intuition of a set. Anyway, so as a consequence of this, maybe I should put it over here. Remember, this was the class of all sets. This was the class of sets which are not members of themselves. We have this, Russell's class, which we mentioned at the very beginning. This is the class of sets which do not belong to themselves. It's the class of all sets because no set belongs to itself. Okay, so this is one consequence of axiom of foundation. You can prove these. Now, I'm going to introduce an important operation. Okay. We're done with axiom of foundation. I mean, we're going to come back to this towards the very end. We're going to basically draw the picture of the set theoretic universe. We're going to somehow build this guy. I shouldn't really say build, but we're going to construct a hierarchy which gives us the class of all sets. And while proving that the hierarchy we claim that gives us the class of all sets is actually doing what it's supposed to do, we're going to use the axiom of foundation again. So we're going to come back to this, but for now, we're going to stop talking about this. You will, in truth, we're not going to need this axiom for most of the stuff that we're going to do over the next 5-6 weeks. However, I will be using this axiom even though it's not really necessary because it somehow like eases the whole work, okay? I'll explain what I mean when we actually use this axiom. So let's now start talking about natural numbers, but before talking about natural numbers, let's introduce an operation. Let X be a set. The successor of X is the set. Now take any set. Its successor is defined to be that set union the singleton containing that set, okay? So I define the successor of a set to be this guy. Now let's prove a proposition. Let's prove that this operation, well, okay, when I say operation, I don't mean a function in the sense of well-defined relations. This is like, you know what an operation is intuitively. So this defines an operation on the class of all sets. And I'm claiming that this operation is one-to-one, meaning that if S of X equals S of Y, then X equals Y. So let's have two sets. Then successors of those sets being equal means that they're actually the same set. Okay, so this is a one-to-one operation on the class of all sets. Why is this the case? Assume that the successor of x equals the successor of y. Then, okay, this set equals this set. So by definition, we have the following case. X belongs to this union, so x either belongs to y or x equals y. And similarly, this y belongs to this set. So we have y is in x or x equals y, because y is supposed to be over here. Now, if it were the case that x is not y, pretend that x is not y, then I would have, okay, this is not happening, therefore x is in y, and this is not happening, therefore y is in x. If it were the case that x is not y, then we would have x in y and y in x, contradicting the exercise, which is over there. Okay? Thus, x equals y. If it were the case that this didn't happen, then I would have y in x and x in y, but that cannot happen by the axiom of foundation, as you will prove later. Okay, so this successor operation is one-to-one on the class of all sets. Now, this proposition is of no use at the moment. I just proved it because I could. Okay? I mean, we're going to use the successor operation, but we're not going to use this fact at the moment. And you should realize at the moment that I am using the axiom of foundation to prove this. Okay? Because, you see, if there were a set like this, then when you construct the successor of this set, you would get the set itself. Okay? So such a set would be a fixed point of this successor operation. And in some other set theories, such sets might exist, but for like in our set theory, they don't, because we are assuming the axiom of foundation. Anyways, this is the successor operation, and now we can start talking about natural numbers. And this is important, what I'm about to do today. So, natural numbers. Now, what's a number? We have an intuitive understanding of a number. What is it really? Obviously, I'm not going to answer that because people have been asking this question since Plato, okay? If you read Plato's Republic, you'll see that even back then they talk about these issues, like what's the number? So I'm not going to try to answer this question as a mathematical question, but I'm going to set this question, like I'm going to reframe this question so that I can give a precise, like I can give an answer to it. What do I mean by reframing the question? I'm not going to ask the question, what's the number? I'm going to ask the question, how can I represent numbers? You see, in our axiomatic system, like we assume certain axioms, and all of those are about objects in some mathematical universe called sets, okay? So everything in the universe of mathematical objects are sets. So if numbers exist, they should be sets. Then you can object to this, like numbers are not sets. 1 is 1, 2 is 2, like there are like two chalks here. 2 is 2, it's not a set. Then because I don't want to argue with you, I'm just going to say, okay, 2 is not a set, but I'm working in an axiomatic system where everything is a set. So if I were to do mathematics with this system, I have to represent numbers by sets. How can I do that? There are many ways of doing this, okay? For example, the answer I'm going to give you is it's not the only way. For example, Zermelo thought that empty set should be the natural number 0. And then the set containing 0 is 1. Then the set containing this guy is 2, and so on. Zermelo came up with this idea, like I'm going to represent 0 by this, 1 by this, 2 by this, and so on. Von Neumann had a better idea. Why is it better? Because, well, at the moment I cannot explain why it's better, but the reason is, like, the definition I'm going to write down automatically generalizes to ordinal numbers, which we're going to learn later. Okay? So there are many answers to the following question. How can you represent numbers by sets? And when I say numbers, I mean natural numbers. The answer is there are many ways, but people, like, since they were introduced, people have been using von Neumann's definition. Okay? It was a hit back then. Okay? People really like this instead of Zermelo's. So we're going to construct natural numbers as follows. Natural number 0 will be the empty set. The natural number 1 will be the successor of 0. Now, if you apply the successor operation to the empty set, you're going to get the set containing the empty set. 2 is the successor of 1. Now, if you apply successor operation to this guy, you're going to get the following set. The set containing empty set and the singleton containing empty set. But this is exactly 0, 1. And this is the singleton containing 0. Now, if you apply the successor operation to 2, you'll realize that you get the set containing 0, 1, 2. And we're going to define natural numbers like this, simply by applying the successor operation over and over again. Okay, so these are called von Neumann natural numbers, and we're going to learn later that these are precisely finite ordinals, the finite ordinal numbers. So we're going to represent natural numbers by these sets. Obviously, I'm doing some kind of identification, but because we're not interested in the philosophical side of this question, for us, natural numbers are going to be these sets, okay? So when I talk about 2 in future, I literally mean this set, okay? So from now on, these are the natural numbers. Like, these were the natural numbers you knew from primary school. Like, there are some objects satisfying certain rules. You don't really know what they are. Now we define what they are for us. From now on, these are the natural numbers. So when I write things like 2 is a member of 3, this actually means something. And it is true. You see, 2 is a member of 3. Okay? So from now on, natural numbers are sets. They can be members of other natural numbers, and so on. Any questions at the moment? No. Now, if you give me any natural number, give me a natural number. Say something. 10. Okay. Now, I can construct the natural number 10. How? I'm just going to apply the successor operation. But how do I know that when I apply the successor operation, I get a natural number as well? Because if X is a set, by pairing this is a set, and by using the axiom of union, we prove that this is a set as well. So I'm using these axioms over and over again. So if you ask me to construct the natural number 10, I can do it. It's going to take a lot of steps, but I can construct it from the axioms. You can give me another natural number like billion. After applying all the axioms probably a couple billion times, I can construct the natural numbers a billion. But how can I construct all the natural numbers at once? You see, each natural number specifically can be constructed from the 8 axioms we have introduced. But is there a set which contains all these natural numbers? Like, can I construct all of these guys at once? The answer turns out to be no, without introducing additional axioms. Actually, it is a theorem that you cannot prove that the set, there's a set which contains all of these guys with only the axioms we have introduced so far. So we need to introduce more axioms. Before that, let's make a definition. Now, a set X is called inductive if you want two conditions to be satisfied. You want the natural number 0, which is the empty set, to be in X, and you want the following to happen. If X contains a set, then it contains its successor. Okay? Now, let's try to understand how inductive sets look. I have the set X. Let's assume that it is inductive. Because it's inductive, it contains 0. Okay? By the first bullet point. Now, by the second bullet point, whenever X contains a set, it contains its successor. It contains 0, therefore it contains the successor 1. It contains 1, therefore it contains the successor of 1, which is 2. It contains 2, therefore it contains 3, because 3 is the successor of 2, and so on. So an inductive set necessarily contains all the natural numbers. It may contain other stuff here, okay? There might be some other stuff. Maybe there's this part of X which consists of some nonsense stuff, and like this part is closed under the successor operation. It is possible. It is possible that there are other stuff over here. But I know that if X is inductive, it has to contain 0, 1, 2, 3, 4, and so on. Okay? So any inductive set automatically contains all the natural numbers. Now I'm going to define the set of natural numbers to be the smallest inductive set. Okay? The natural numbers will be the smallest inductive set. It's going to be the inductive set which contains all these guys but nothing else. Well, I can define it. I just defined it. This the set of natural numbers is the smallest inductive set. Does it exist? As I said, we cannot prove that it exists without additional axioms. In order to prove that the set of natural numbers exists, or any infinite set at all, we're going to introduce another axiom called the axiom of infinity, okay? And it simply says the following. An inductive set exists. In other words, it says that there exists a set Y such that empty set is in Y and Y is inductive. Okay? I don't know why I changed the places of X and Y. So there exists a set Y such that it contains the empty set, it contains 0, and it's closed under the successor operation. So it's inductive. So that is, we have this. Now, why is this called axiom of infinity? Because, as you can see, whenever an inductive set exists, it has to contain all these guys, so it has to be infinite. We actually haven't defined what it means to be infinite. We're going to work the other way around. Like, we're going to define being infinite in terms of natural numbers, but you intuitively see that any inductive set is automatically infinite. So this is why it's called the axiom of infinity, okay? So it says that, it roughly says that there is at least one infinite set. It doesn't really say that. It says that there exists an inductive set. And this difference is important. I recently saw an article about mathematical education by an actual mathematician, like a guy with a math PhD, who really didn't know that much set theory, and he claimed that like we're defining infinity in terms of, we're defining being infinite in terms of natural numbers, and we're defining natural numbers in terms of being infinite. That's not true, because he was under the impression that the axiom of infinity says there's an infinite set. No, that's not true, because like the word infinite set is already defined in terms of natural numbers. So if you try to define x, like if you're saying that an infinite set exists, like thinking that this says an infinite set exists, people will ask you, what's an infinite set? Then you will have to talk about natural numbers. So you're going to say that a set is infinite if it's not a bijective with a natural number. It's not a bijection with a natural number. And then you have to define what natural numbers are. But in order to do that, you have to construct a set of natural numbers, and that requires the axiom of infinity itself. So for him, the argument looked circular, so this is why he was against it. But as I said, he didn't know what he was talking about. So the point is, the axiom of infinity says an inductive set exists, and now we have at least one infinite set. Now let's define a set of natural numbers. Let J be any inductive set. Okay? I take an inductive set. As I said, an inductive set may contain more stuff. Like this axiom only says there's one inductive set. I don't know whether it's a set of natural numbers or not. It may contain other stuff. I want to get rid of this part. I want to clear this part. By the separation axiom. Now, if you use the axiom of separation, the following class is a set. Which class? I'm taking all elements of this inductive set which belong to every inductive set for all I. Now, I don't want to write this in terms of with a formula in the language of set theory. It's going to be too long. You know what this means. Inductive means that it satisfies this. Okay. So this implies X is in J. So I'm taking all elements of J which belong to, oh, this is I. I'm taking elements of J which belong to every inductive set. So intuitively, this is the intersection of all inductive sets. Okay? Because if you're looking at the set whose elements belong to every inductive set, then you're simply taking the intersection of all inductive sets. Okay? Of course, I can't write, like, I can't form this intersection because there are like the class of all inductive sets. It's a proper class. It's not a class. So I can't simply say that this is the intersection of all I where I is inductive. You can write this down, but then people are going to ask you the following question, like, why is this a set? You're trying to take an intersection where these guys range over a proper class. This might not be a set in general. So here's how you get around this. You fix an inductive set. You know that this guy has to intuitively contain all the natural numbers, and you're taking the elements of this set which belong to every inductive set. So this is the set of, this is intuitively the intersection of all inductive sets, and we define this to be the set of natural numbers. Okay. This is defined as the set of natural numbers. So the set of natural numbers is, it's the smallest inductive set. Maybe I should write it like this. I'm putting this quotation marks to indicate that, like, this is not completely formal. What does it mean for a set to be the smallest inductive set? It exactly means this, okay? So if this formalism bothers you, think of n as the smallest inductive set or as the intersection of all inductive sets. Questions about the set of natural numbers? Now, I know that there is a set which contains this guy, this guy, this guy, this guy, and all these guys at once, okay? Yes?
What is the successor of natural number?
It is this set. If you take, okay, this is the set of natural numbers. If you take the successor of this, you're going to get this guy. You're going to get a set which contains all the natural numbers and the set of natural numbers. In future, we're going to give a name to this. This will be called omega plus 1. Okay, this is the successor of this ordinal. This will be called an ordinal number. It will be called omega. This will be called omega plus 1. We're going to talk about that. After constructing natural numbers, we can keep taking the successors. Okay, and we can construct those sets. Those are going to be important. Other questions? Now, let me prove something which you've been probably using since high school and whose proof you are probably seeing for the first time. I'm going to prove the principle of induction, okay? Now we're going to prove induction, but first we have to state it. If I is a subset of natural numbers, which is inductive, then I equals n. Now, I have a subset of natural numbers which is inductive. What does it mean for this set to be inductive? It contains the empty set, namely 0, and whenever it contains an element, it contains a successor, right? But I assume that this is a subset of natural numbers, so the elements of this guy are already natural numbers. So this set being in, like this set satisfying this property is the same as this. If some natural number is in I, let m be a natural number. So this is a potential element for this guy. I want this. If n is an I, then the successor of n is an I. I'm not writing here m plus 1 because we haven't defined addition at the moment. So a subset of natural numbers being inductive, it means it contains 0, and whenever it contains a natural number, it contains the next natural number. I'm claiming that such a subset should be all of n. Now, you used this principle before, okay? You were proving things like this. What is this? This is like n choose 2, right? How did you prove this? You showed that this is true for 1. Yeah, let's start with 0. You showed that this is true for 0. Then whenever it's true for some n, it's true for the next n, and blah, blah. What you really did when you proved that was the following. You took a set of all natural numbers such that this holds, okay? Like, when you do induction arguments, at the back, what you're really doing is the following. Let's think of the proof which shows that this is true. Let's think of the proof which shows that this is true by induction, okay? What you're really doing when you do that induction proof is the following. You're constructing this set. You're taking all the natural numbers satisfying whatever you want to prove. And then you show that this set is inductive. If this set is inductive, by this theorem, it is the set of all natural numbers, which means that this is true for all natural numbers, okay? So this is the usual induction you knew before, except it's written in a more fancy language. Now let's prove this. Okay. The proof is like one line. By assumption, I is a subset of natural numbers because that's by assumption. Okay? Okay, let I be such a set. Then, that's by assumption, this is a subset of natural numbers. On the other hand, the other direction is true simply because n is the smallest inductive set, okay? And by definition of natural numbers, the natural numbers is a subset of every inductive set. Since n is a subset of every inductive set. So I equals n. So there are two directions, there are two inclusions. One inclusion is given to us as a subset of natural numbers. The other direction simply follows from this assumption that I is inductive, because natural numbers is a this definition immediately implies the following: natural numbers, it's a subset of I whenever I is inductive, okay? You can easily show that this statement follows from this definition. Under this definition, natural numbers, every natural number belongs to any inductive set. So this direction is true for inductive sets. And so induction is true, okay? Now, let me prove something via induction. Oh. Let me put a couple of remarks. You see, over here, no, this is fine. Let's leave it as this. This is fine. Let me prove something via induction. We're going to talk about this later, but I want to show you one example of this today. Let's define the order. Let's define a relation on a set of natural numbers. Definition: let m and m be natural numbers. We define or. We define the relation less than on natural numbers as follows. I'm defining a relation on the set of natural numbers. I'm defining it in the following way. M is related to n under this relation if m is a member of n. As you can see, I used the less than symbol, so this is going to be the actual ordering on the set of natural numbers, but at the moment we don't know that this is an order relation. We shall prove later that this is a strict well-order relation, okay? That's going to take some time. We're not going to do it today, but I just want to define this so that I can show you the following. Lemma, which one do I want to prove? Okay. Now I'm going to prove something very simple. And it's going to be embarrassing for us if someone just watched this videos like from this moment without knowing all the previous stuff. Because I'm going to prove that 0 is the least natural number under this definition. for every natural number n in n, we have that zero is strictly less than n or 0 equals n. Or maybe I should do it like this. 0 is less than or equal to n. Remember, this is defined to be a is less than or equal to b if and only if a is strictly less than b or a equals b. So let's prove that 0 is the least natural number. Now, how can you prove this? Remember the definition of natural numbers one by one. It was obvious, right? I mean, 0 equals itself, so there's no problem. One is the set consisting of 0. 2 is the set consisting of 0 and 1, and so on. Like you saw on the picture that 0 belonged to every natural number. Now, I want to prove this. I want to prove that for every natural number, I have the following. Either that natural number is 0 or 0 belongs to that. How can you prove this? Now, how do we define natural numbers? As we define it as the smallest inductive set. And from that definition, it followed, the principle of induction followed. Anything you need to prove about natural numbers, okay, I'm taking that back. 99% of the things that you want to prove about natural numbers, they are actually proven by induction. Take this very, very trivial statement, 0 is the least natural numbers. We can prove this by induction. Let I, why am I doing this? I just want to show you how an induction is written more formally in this setting. I want to do induction. I want to prove that this is true for all natural numbers. So I do the following. I construct the set of natural numbers for which what I want to prove is true. Now, I want to show that this set is inductive. Okay, I want to prove that I is inductive because if I can show that this is inductive, then by principle of induction, this equals the set of all natural numbers, which would mean that this is true for all natural numbers. How do you show that a set is inductive? You need to show two things. Let's first show that the empty set 0 belongs to this. Clearly, 0 is an I as 0 is less than or equal to itself because everything equals itself. Okay, so 0 equals 0, so 0 is an I. Now, let n be a natural number and assume n is an I. Now, I want to show the second property here. I want to show that whenever a natural number is an I want its successor is an I. We want to show the successor is an I. As n is an I, we have the following. Either n is 0 or 0 is in n, because we define this to be simply the membership relation. Okay? In both cases, we have that 0 belongs to the successor. Because if 0 equals n, then 0 is in here. So this is true. If 0 is a member of n, well, 0 is a member of n, and this I'm defining this to be n union something, so this is true. So in both cases, this is true. And thus, and so, 0 is a member of successor of n, therefore it's strictly less than the successor of n. Thus, Well, successor of n satisfies this, thus the successor of m belongs to I. Therefore, I is inductive, and hence, and by principle of induction, I equals n. Therefore, this is satisfied by all natural numbers. Now, I'm not going to write down my induction arguments in this much detail in future. I just did this for this very basic example so that you see how these are written properly. But in future, I'm just going to take a shortcut and do induction as you used to do, okay? But in reality, what's happening is this. You construct the set, you then show that that set is inductive. How? You show that 0 is in that set, and you assume you show that whenever a natural number is in that set, the successor is in that set. Okay? But in future, I'm not going to write this much. I'm not going to write this many words on board. Is this understood? Now, I could have proven something via induction. Why have I chosen this statement? Because it's really simple. As I said, almost 99% of the stuff we're going to claim about natural numbers, it will be proven by induction, okay? For example, I'm going to claim that this is a well-ordered set. We define this less than relation by membership relation. I'm going to claim that next lecture, this is a well-ordered set. In the proof, you'll see that I'm just going to keep using induction over and over again, okay? And that's not surprising because think about the definition of this. How do we define this? We define this as the smallest inductive set. So by nature of the set, anything claimed about this should be proven by induction because this is supposed to be the smallest inductive set. I mean, there's a reason that this proof is 2 lines. The core of the proof comes from this claim, and is a subset of every inductive set. So it's no coincidence that anything about natural numbers is proven by induction, okay? Now, before we conclude the lecture, you should realize that for us, the principle of induction, it's not a principle really, it's a theorem, okay? It's a theorem which follows from the definition of n. So we are able to prove the principle of induction. If you take a philosopher and ask about principle of induction, he or she will tell you another principle, which is basically generalized to more stuff, not just claims about natural numbers. And he or she will tell you that the principle of induction, it's not deduced from something, but it's like a principle that you simply start with. In a sense, that's true, but for us, it's not. For us, principle of induction, it's a theorem, which follows from the definition of natural numbers. And why does this exist? Because it exists because of the axiom of infinity. So everything comes back to axioms. All this is happening because of the axiom of infinity. Anyway, the point is, this principle of induction and the principle of induction that philosophers talk about they're not really the same. They're similar, but not really the same. Okay? So if you grab some guy from the next department and say that we proved the principle of induction, if he or she is reading Hume, then he or she will be very sad, okay? But we can actually prove it. Anyway, so let's finish the lecture. Next lecture, we're going to prove that the natural numbers with this relation is a well-ordered set, and we're going to prove more stuff. We're going to start talking about the arithmetic on natural numbers. So I'll see you on Thursday.